Hello and welcome back. Today's session, we are going to talk about another system design use case. How can we design any of the cloud file upload system? So we can take an example like Apple AirDrop or Google Drive or maybe Dropbox, or we can say like Microsoft or OneDrive. These are a very similar system. All are storing the file into the cloud system. AirDrop is the Apple's AirDrop, so you can always upload any file into the iCloud system, and you can use the Google Drive to store the file into your Google Cloud system. A Dropbox you can use. This is one of the tool which is coming from a proprietary, and also Microsoft OneDrive, right? So this is these are the very similar kind of use cases. So what exactly the AirDrop happens? How this AirDrop really works? So before getting into the actual topic, I would request, if you haven't done it, please subscribe the channel and click the bell icon so that you can get the latest update whenever we are uploading any new videos. Thank you so much. So how, if we think of the AirDrop or Google Drive, how it happens? AirDrop is nothing but a file upload client, so which really helps to upload a file into the cloud system. So here is the AirDrop, and here is the iCloud. So what it happens is, whenever any file drops into this particular client, so it try to upload the file into the cloud system through network, right? So this is very simple. That's fundamental functionality what it happens. But this is what it's the very basic thing. But behind the scene, there are a lot of things happening. When we talk about the AirDrop or maybe the Google Drive also, Google Drive, how it happens? There is a Google Cloud storage. So whenever any file drops into here, the file goes it getting stored into the Google Cloud storage through the network, right? So that's how it happens, right? So now it's a big you know it's a bigger use case altogether, but we'll focus on how this client itself is working, right? How it's getting stored into the cloud system. So that's what our focus is. So our focus is, let's define our focus. The functional requirements, if we say, like, we the system should able to upload the file, and it should update file, and should sync to all devices. So if you see, this is what the case is. Like, let's think of the AirDrop, right? The AirDrop itself, what it does is, like, once the file is stored here, then this file, if a particular user has a computer or a phone or a tab, right? Tab. So what it will happen? It will all sync to all the devices, right? The same file. If this is the file one will be here, file one will be here, and file one will be here. Whenever the user will log into the any of the system, any of the devices, right? So that's how it happens. So this is what the system, it talks about the syncing, right? And this is the update whenever any file being updated. So how it will be control the updation of any file, right? And uploading files. So whenever we are user uploading any file, so that should able to store into the cloud system, right? The cloud storage system. So this is what we're going to design, what exactly the actual technique behind the scene it happens. So we are going to design that. So we are not going to keep in mind, like, we are not going to design the AirDrop itself, or the Google Drive itself, or the or Dropbox itself, right? We're trying to build a new system which works like that, right? Focusing on the specific requirement we have, right? So that's how we are going to build it. So let's do that. Whenever user try to upload any file, so there is a device uploaded a file. Let's file called F1. Okay, F1 with size of 10 MB iCloud storage, right? So when this file F1, the user will drop the file 1 into the AirDrop. So this will automatically try to send the file to the cloud storage through the network. This is the F1 with 100 MB, correct? So 100 file. So here, so 10 MB file, right? 10 MB file. So it will be getting stored here, F1 with 10 MB, right? When it will send another file called F2 with maybe 5 MB, so it will again go through the same network path, okay, with F2 5 MB, right? 5 MB, and it will be stored somewhere here, 5 MB, correct? That is F2. So now what it will happen is if the user did some changes into the file F1, right? What it will do? So it will try to send the file of again the whole file, uh, the F1 delta to the system, and it will create another 10 MB file of F1, right? So what is the problem you are seeing here? So the problem is, like, we already sent that particular file F1 to the cloud system, right? But whenever any update, even if we are just changing a character from maybe A to B, just a character, but it has to really send the whole, whole file to the cloud system. Even if there is a very negligible change into the file, but it has to really consume 10 MB of the network bandwidth, right, to send the data to the cloud system, right? It blocks the bandwidth for other uploads or other updates, right? So that's the problem here, right? So if, for example, there are millions of users that are trying to upload the file, and for that, for if everyone, it on an average, there will be on an average there is a 20 MB of file getting uploaded. If 1 million upload happens, then there will be 1 million into 20 MB. That much bandwidth you need to maintain to handle all these file uploads. Rather, we can have one mechanism called multi-file offload. Right? What does that mean is, while we are offloading a particular 10 MB of file, so if we can split this particular file into multi-parts in the sense like multiple chunks, then it will be easier to upload. Ultimately, this 10 MB file will be converted into maybe 5 chunks, 2 MB of file. So it will be 2 into, it will split into 5 splits, 2 MB each, right? 2 MB each. So what it will do now the bandwidth usage reduced 5 times altogether, right? So that means, instead of sending 10 MB at a time, we are sending 2 MB, 2 MB, 2 MB at a time. 2 MB into 5 times, right? 5 times. So that the network bandwidth usage is, significantly lower comparing to the actual file size, right? So that's the one thing we can take into consideration. Split file into smaller chunks. But when we are splitting this file into smaller chunks, then there is another problem comes in picture. What is that? So how we can really manage, like, how will tell the system, like, okay, whenever we are sending the chunk, those chunks are related to a specific file, right? So that whenever we that particular file will be downloaded, so that has to combine all the splits and download as one file, right? So that's how it supposed to be. So to maintain that, we have to have a system to deal with all those metadata, right? So to deal with that, there should be a metadata system which will hold the metadata related to the particular file, how many splits and all. So whenever the file will be splitted and sent to the cloud, the same time it will also send the metadata information, metadata for maybe file 1, and it will hold the splits, all the splits related to that particular file, and store it somewhere, some database system. So that's how it will do. Whenever it's going to download, it will first check, like, what is the file user trying to download, and what are the split information it's available, right? So it will gather all those split information and combine that file and download it to the user's machine, right? So that's how we can manage the metadata system, right? So managing the metadata system is easy and also not easy, because when it comes to the millions of metadata requests storing to the metastore, then how it will handle. So we can put some mechanism called some queuing mechanism over here, right? Which where the metadata will be queued over here for multiple requests, right, or multiple files, correct? And then it will try to store into DB. Whenever we are choosing any metastore, so the metastore has to be good enough to support the ACD, because in this ACD role, right? So because in this case, what it happens usually, whenever we are making it split and sending that to the storage, the metadata also has to be consistent and it has to be sequential, right? Sequential in the sense like there should not, if you are sending split 1, the split 1 should be there, and the split 1 should be, split 2 should be next to the split 1, right? So there should be a mechanism to connect all the splits sequentially, right? Split 1, split 2, split 3, maybe so on, right? So whenever we are storing those, sequence must be there, or in the all the transactions has to be consistent, in the sense like when we are storing this file into the iCloud, and if someone is trying to download that at the same time, if all the splits has not been persisted into the DB, then the user is trying to download the file will get the wrong data, right? Or the wrong file with wrong splits, right? If the split 1 is already stored, split 3 is already stored, and split 2 is not stored but not yet stored into the metadata system, then what will happen? Whenever the user trying to download this file, it will only send the split 1, split 3, split 2 will be missing. So in that case, there will be a data miss, or the inconsistency of the data in between multiple devices or multiple user or multiple requests, right? So for that we have to consider such data store, which really gives the benefit out there regarding the consistency. So if that is the case, then definitely we can go with some RDBMS system. Maybe think of MySQL. We can also go with NO-SQL system. As we know, like NO-SQL system always eventual consistency, right? Eventual consistency. That means we have to have mechanism, or we have to have a different service to handle those consistency and the sequence of the split to maintain and deliver it. So that's how think of or build a different system altogether, a different service altogether, right? So let's, for the time being, let's go with the we can consider the MySQL. So now metadata system is there, which will receive the request and receive the metadata system, okay, metadata for any file, and store it into a metastore system. So that's how the metadata system takes care of. So now we have things in place like to handle the upload and handle the metadata system. Now let's focus a little bit on the actual service side of the house, right? What exactly service? The service is the AirDrop, or the Google Drive, or whatever the client we are going to build. So if we focus a little bit, go in depth for this AirDrop itself. So this is the AirDrop service, right, as a client, or maybe Riva, or maybe Dropbox client. So how it happens? So it's already installed in all your devices, right? What it will do whenever that particular client is being installed or available in the storage, what it creates, it usually, what it happens is it usually hold one thing. We have to have a system called the splitter. Splitter is nothing but the service which will split the file into a multiple chunks. So one file will be divided into multiple chunks and try to send to the network, right? So now, and another thing, once the file will be split and try to upload into the cloud storage, then what it will happen? It has to have the metastore system to deal with different files we are going to upload, right? So for that, there has to be a local DB store. So that means whenever we are uploading that, at the same time, the splitter also has to hold the metadata related to that particular file over here, right? and then so whenever it will hold, so the moment it's trying to send to the storage, it will also send the metadata meta information to the metadata system. Now it's able to upload the file, able to send the metadata to the metadata system as well. So now if it happens in one device, then there should be, so the same application also installed in the different device as well. So how it will sync the file? So there has to be the syncer service, right? The syncer should take care of like syncing the file. I mean, it keep watching, or you can say watcher, keep watching the file from the cloud and try to download that into the local file system. That's what the syncer will or watcher will do. To sync this, right, it will always keep referring to this database, I mean, the local database, or here, or it can directly talk to this metadata system, right? Metadata system to really get the file information with whatever the file is trying to sync to the local. So it will try to get those information from, I mean, metadata system, and try to download that from that particular, try to sync that particular file to the other devices, right? So that this watcher will take care of that. So this is how the internal system we could design to deal with the data upload, data splitting, and storing the meta information, and building the sync service. So this is how it can be. So in a nutshell, how the metadata request happens, like, so here is the maybe device 1, device 2, maybe device 3. So everyone sent to the queue, some message queue system, we can say the RabbitMQ or Kafka or some kind of resilient message queue system, right? Message queue. And once this will go to, I mean, the request will go, okay, the request is metadata will go to the message queue, and this message queue, and there is metadata service. So the metadata service is already subscribing to the message queue, and it will process it and try to store into a metastore. So we can say metastore. So this is how whenever any file gets uploaded, then how the metadata goes through the flow, right? So the request comes from the client from every device, and it comes to the message queue, and from the message queue, it's the metadata service is already available, that already subscribing to the message queue. And once it will get the message, it will try to process the data and store into the database. How it will store and what are the different information it will store, we are not going to touch about that at this point, but this is what the flow, it will try to store some meta information into the system. So when it's try to sync those, so how it happens, let's for example, when it's try to sync as well, this is request message queue, and there will be a response message queue, response. So this response message queue, whatever it will do, so whenever it will try to, so there are syncers available, syncer service available in every device, right? So what it do, whenever it will try to sync it, so it will, this guy is subscribing this channel, right? This channel. So when they are subscribing, so the moment any metadata comes in the DB, so for the syncing side of the house, so every device has the syncer service. So that syncer service is already subscribing to a queue. That's we can say that a response queue. In that response queue, where data will come from. So the metadata service, whenever it will get any data from the request queue, it will try to store it, and at the same time it will try to send the same meta information to the response message queue. So the moment any message available in the message response queue, then the syncer will just sync it and try to update the local data store, right? So that it will able to get those updated information available in every devices. So it's for every services, right? So we can say otherwise. So it can be like this. So in a nutshell, how it will happen, I mean, the whole flow, right? The whole flow will be something like this. So here is the airdrop. Let's we are let's uh, let's talk about the airdrop itself, airdrop client. So airdrop client, what it will have end of the day, it will have a splitter, right? Service called splitter, and the DB in the watch, or maybe syncer. So whenever file drops into here, then what it will do, it will send a request. Okay, it will call an API, maybe we can say API, okay, or request API to upload, right? Upload. So this is a file upload service application, or we can say the application server here, right? App server here, right? So app server is sitting here. Now what it will do, this app server is responsible to just store the file into the iCloud system, iCloud storage. So now there is another system and another request going to a different route related to the metadata, right? So for this metadata, so there has to be a metadata service as well. That's also metadata service. So what it will do, it will get those metadata detail and send to the metastore, right? Metastore DB. But here is, so this will be the whole, so here it will go to the metadata, and the metadata request will, meta information will go into the message queue, and from the message queue, so it will go to the metadata service, right? Service, and from that metadata service, it will store into a metastore. So that's how it will happen when we are uploading the file. So for the downloading also, what we have discussed is the moment it will be stored here. So the metadata service also send that put that particular message into the queue. So that we already talked about that response queue, right? So the moment it will available here, so there is a notification service running here, right? So the moment the notification service will see like there is a message available, so it will try to send that particular message to the syncer, right? So it will be keep syncing the data, consistently, and keep syncing the data continuously. The moment it will notify the client, the client will try to sync that particular metadata here as well as the file, right? So that's how this is what the complete design for that whole service will think of. So this is what the whole complete service will be, correct? So now, if we are talking about a single device here, maybe there might be multiple devices. It work at the same manner, right? So there will be another device here. There will be another device here as well, right? D2, D3, and same thing happens for here as well, right? And when it's and the syncing service also happens for this. So that's how it happens. But so this is very the whole architecture we are talking about and designing a file upload service. But what about scale? We didn't talk about the scale at all. So for scaling, let's for example there are 10 million user per day, right? Active users, and for every user can upload every user on an average there are five files they can upload, right? So for 5 files and 10 million, so that is 10 million into 5 number of requests, right? Request for day. So that's how, then that is 50 million, right? 50 million requests per day, right? So that means what will be the traffic will be 50 million divided by 400 seconds, so equal to what? The number of the total number of requests we are going to get per second. That's how it will be. Then the whole system has to handle, the whole system should capable enough to handle all these big amount of requests to the system. For that, what we can have the system in place is, as we know, like the different components available in our system, for a system design. So that we already talked about in our previous one of the previous session, related to the load balancer and the message queue and APIs, can say like cache and all, right? So in that case, what is the component we can really incorporate here to handle those high volume of requests, right? So for that, what we can have is we can place a load balancer here itself, right? Load balancer, right? So what it will do, whatever the request from the multiple millions of or billions of devices sending request to store the file, then this load balancer will handle all those the complete system, right? And then we can have another load balancer somewhere here to send a request, right? Request to the system, the metadata system. Applying the load balancer itself, we can really handle the whole bunch of requests we are getting for second. So that will be easily mitigated, right? And the performance wise, it will be better. And another thing is how fast we can get those data while we are seeing like writing and reading. So when uploading, we are writing the file, right? When reading, that should be fast enough as well. So in that case, we can really incorporate the caching for this system, so that what we can do, the total number of data, the total number of records we have stored here for any file or any bunch of file, some of the information can be stored into the caching, so that it can be it can be increase the performance and lower the latency. So how we can decide like what should keep in the cache or what shouldn't? So we can go with like 80-20 rule, or maybe 75-25 rule, whatever. That means if we have total number of request available 100%, then 20% of that, the total data available in the meta store can be stored into the caching system, right? So in that case, if we have, if we have 100 million records available in the meta store, then we can 20 million we can store into the caching system. Once we'll store those amount of data into the caching, then how can we refresh the cache? So that is another topic. But refreshing the cache, there are multiple algorithms and techniques can be used to implement the caching. So those are the things we have already discussed in our previous session. So that's related to the system design and fixtures. The caching here, we can maybe use LRU, right? Least recent use, right? So least recent use, we can really evict those particular entries from the caching, and we can refresh the cache itself with the new data itself, right? So that's how we can implement the caching over here. When all these things comes in picture, the file and data, the security cannot be ignored, right? So the security also need to be applied. And thus, how can we apply the security? One way we can apply the security, like security in transit, right? In the sense like while we are sending the file is going through the network. That file, the first thing is can be encrypted. Encrypt the file, encrypt the data on the transit, so that whenever it will transitioning through the network, so it will encrypt it and it will store into the iCloud storage. And when it's trying to download and sync to the system, the client should have capable enough to decrypt the data. So that's where we can apply one of the security on the data if the data has some sensitive information and all. So that can be secured by encrypting the file or data itself. That is a very one of the security we can apply on top of that. There could be different way of implementing the security system for any system. You can go through our previous video that's talk about security as well, how we can implement security in any of the system design use cases, right? So this is how we can really implement the whole file upload system, okay, or file uploader system. This file upload or file uploading cloud storage is a bigger use case altogether. So we are just touching some portion of that particular whole use case, but I think this is good enough to think more about the use case, how we can make it more performant and how can make it more resilient. And thank you so much, and that's it for now. And thank you so much for watching the video. And again, I would requesting, if you haven't done it, please subscribe the channel and press the bell icon to to get the latest updates. Thank you so much. Stay safe. Update one.